Hello, a very good morning to all. And today we are going to start our new chapter that is a coordination chemistry, right? So, this is very important chapter. And one important note here now, this is a very easy chapter. If you understand the concept behind this chapter now, then you are able to solve each and every question related to this chapter, right? So I'm going to explain in today's session, I'm going to explain each and every term related to this chapter and try to solve many PYQ as we can. Okay, so this chapter really going to help you a lot, and if you understand the concept, then you easily get 8, okay, 8 to 12 marks alone from this chapter. Every year, 1 to 2 questions or maybe 3 questions definitely coming from this chapter, right? So let's start with the today session, and it's going to be very interesting, right? Okay. So, first of all, we are going to see some basic concept, basic terms, and the theories of the coordination chemistry. And later on, we are going to discuss PYQ questions, right? Okay. So, let's start with this chapter. Now, what is this coordination compound, right? So, before understanding coordination compound, we must know what do you mean by the double salt. So, I'm giving here a quick revision of the every topic related to this chapter and summarize in 30 or we say 30 to 35 minutes, and rest of the 15-20 minutes we are going to do PYQ question, right? Okay. Now we know that that is a Mohr salt, potash alum, and kernite. They all are the examples of double salt. Okay. For example, Mohr salt, it contains two salts, that is ferrous sulfate as well as ammonium sulfate, and same as the potassium. So they are called double salt. On the similar way, what is ethane 1,2-diamine and oxalate are a didentate ligand. So what is this ligand beta? Actually, coordination chemistry is all about metal ligand bond, right? So metal is what? Metal is like a which accept the pair of electron, and ligand are the electron pair donors. So whichever substance donate electron pair, they are known as ligand, and the metal are electron acceptor. Okay, so ethane 1,2-diamine, as we can also write ethane 1,2-diamine as EN, right? So ethane 1,2-diamine and oxalate, that is C2O4, are the didentate ligand. Didentate ligand means what? If I'm talking about ethane 1,2-diamine, the structure of ethane 1,2-diamine is like this: NH2, CH2, CH2, and NH2, and having lone pair of electron, right? So what we mean by the term didentate? Didentate means two donor group. That is, a ligand having two donor atom is known as didentate ligand. For example, if I'm talking about ethane diamine oxalate, it having two donor atom, right? This nitrogen also having lone pair and it will donate the electron, and this nitrogen also having lone pair, so it is also donate electron. So ethane 1,2-diamine and oxalato are known as didentate ligand, right? Similar EDTA, that is ethylene diamine tetraacetate hexadentate. It means they have a six donor atom. Okay, they have a six donor atom. It means they are containing two nitrogen and four oxygen donor atom. So out of total six donor atom, two is from nitrogen and four oxygen are act as a donor atom. So I hope is it very much clear what is unidentate, what is bidentate. Unidentate means what? Which having only one donor group. Bidentate, didentate means two donor group. Tridentate means three, and so on. And EDTA falls on the category of hexadentate ligand, means having six donor group, right? Okay, so let's start. Okay, next is that is the compound which chelating ligand are more stable than complex compound with the unident ligand. If I'm talking about the chelating ligand, what is this chelating ligand, beta? Chelating ligand means which form cyclic structure, right? If I'm talking about that is En. So out of En, if I have a that is Fe and En type of complex. Okay, so out of these FeEn, and if I have a complex like FeCN6, okay, that is FeCN6, and out of these two, if someone asks which one is more stable, then always remember one thing: the ligand which is chelating in nature are more stable as compared to unidentate ligand. What is the term chelating ligand here? Chelating ligand means the ligand which forms cyclic structure. Okay, so ligand which form cyclic structure are more stable as compared to the unidentate or we say monodentate ligand. Right now, the next important term now, NO2 negative and SCN are called ambident ligand. Okay, so what is this ambident ligand, beta? What do you mean by this term ambident ligand? Ambident ligand are example, some many more example of ambident ligand like NO2, SCN, similar cyanide and NC. They all are the example of isocyanide or ambident ligand. What do you mean by this term ambident ligand? Ambident ligand means a atom or we say a molecule having two donor atom, but at a time only one can donate. Okay, if I'm talking about NO2 negative, both NO and O2 have a tendency to donate lone pair of electron, but at a time either N donate or O donate. If I'm talking about CN and NC, both having tendency to donate the lone pair of electron, but at a time either carbon donate or nitrogen donate. So these type of ligands are known as ambident ligand, right? Very good. Now, beta, if you have any doubt now, please ask me in the chat box. Okay, I'm going to reply each and every queries of you, right? Okay, the next is CONH363 is a homolaptic. What do you mean by this term, beta? Homolaptic. Homolaptic means if the coordination complexes, if the ligand are same, it means if only one ligand are we use now, for example, in this complex only NH3, there are 6 atom of NH3 we use, then this type of coordination complex is known as homolaptic. If we use different ligands like one is NH3, one is Cl2, one is Br, such kind of ligand, if we use different kinds of ligand, then it is known as heterolaptic. So this point also important, try to remember this: homolaptic ligands and heterolaptic, right? Okay, now the next point is, if I'm talking about the IUPAC name, so this one is also very important. So here I'm sharing a one small trick with all of you, that how to write the IUPAC name of the complex, right? So just write the what is the trick to write the IUPAC name? Just follow this trick and you are able to write the IUPAC name. First of all, write the name of active metal, right? Name of active metal. So first step is write the name of active metal, right? Then write the name of number of ligand. Number of ligand, like whether it is a di, tri, hexa, tetra, right? Number of ligand. Then name of the ligand. Then write name of ligand. Okay, clear? Okay. After this, name of the active metal is done, number of ligand is done, name of the ligand is also done. Then write the central metal atom. Okay, central metal atom. And last, just write the oxidation state. Always write oxidation state in Roman. Okay, so always write oxidation state in Roman. So these are some basic tricks. By using this, you can write the name of the any coordination complexes. Okay, here what do you mean by this term active metal? Huh? Later I am going to give example and you understand this very easily. Okay, now if I'm talking about this complex, that is NiCl2 PPS3 twice, what is the name of this complexes, right? So here we know that nickel is a metal and chlorine and PPS3 twice is a what? Is a ligand. So here there is no active metal. Active metal means what? If some metal like group one metal or group 2 metal which is outside the coordination sphere, right? This square bracket is known as coordination sphere. So if some metal lies outside the coordination sphere, then it is known as active metal, and it is generally from group 1 or group 2, either it is sodium, potassium, like that. Okay, so if there is no active metal, then just leave this. Now start with number of ligand. Now here two ligands are there. One is a chloro, one is a PPS3 twice. So out of these two, always maintain the alphabetical order. So if I'm maintaining the alphabetical order, then chlorine would be preferred first. Okay. So what is the name? That is a dichlorido. Whenever the ligand is inside the coordination sphere, now always replace E with O. if some ligand nature, for example, if I'm talking about chloride, chloride, what is the spelling of chloride? Chloride means CHLORIDE. Whichever ligand whose name is end with E, just replace this E with O. If I'm talking about chloride, its name become chlorido. If I'm talking about fluoride, its name become fluorido, and so on. Okay, right. So what is the name here? That is a dichlorido. And in case of such ligand which always already having a name like, for example, if I'm talking about En already having name ethane 1,2-diamine. So for such kind of ligand, use the term bis for 2, thrice for 3, and so on. Okay, so this having already numbering is prepared, so we use the term bis. So this is a dichlorido, and this is bis triphenyl phosphine, and nickel having oxidation state of what? 2, because this having a 0 oxidation state, right? And Cl having -2 oxidation state. So total oxidation state in nickel become +2. On the similar way, just try to write the name of this complex. For example, this is also, first of all, you have to write the name of the ligand here. Aqua for water and amine for NH3. So according to alphabetical order, which will lie first? Amine or aqua? Obvious, it's amine. So write triamine, because here 3 amine groups are present now. So triamine, triaqua, and chromium. H2 having 0 charge, NH3 also having 0 charge. So where the charge is chloride, that is -3. Now, one important note here. Here, the chloride atom is outside the coordination sphere. If the atom is outside the coordination sphere, then we can write as its normal name, like chloride only. Okay. If it is present inside the coordination sphere, then we can call as a chlorido. Okay. If they are present outside the coordination sphere, then we call it as a normal name, that is chloride. So this is the name of this, right? So this is how you can write the IUPAC name of the complexes. I hope, is it clear to all? Yeah. Is it clear to all? Anyone having any kind of doubt? No? Shall we proceed? Okay. Now, the next is tetrahedral complexes not show geometrical isomerism. So these points are also going to be very, very important. This is for optical isomerism or geometrical isomerism. So this is, I'm talking about the isomerism part. Like, so tetrahedral complexes do not show geometrical isomerism. This point must be remembered, beta, right? Now, if I'm, because in coordination number 4, now we have a two different possibility. Either it will be sp3 or it will be dsp2. sp3 means having shape tetrahedral, and dsp2 is mean square planar. Okay, so coordination number 4 having two cases, that is sp3 or dsp2. So tetrahedral complexes do not show geometrical isomerism. Square planar complexes of the type Ma2b2 and Ma2bc and MABCD show geometrical isomerism. So just remember this, a square planar show geometrical isomerism, but only these three types, that is Ma2b2. What is here A2 and B2, beta? A2 and B2 means ligand. Okay, A2 and B2 means ligand. Like if I'm talking about, this is Fe and this is En2 and this is Cl2, like that. Okay, so these are the ligand A2 and B2. So square planar complexes of this type show geometrical isomerism. Now, one more important thing, beta, that is a square planar complexes containing asymmetrical bidentate ligand. Square planar complexes containing unsymmetrical bidentate ligand, that is MAB2, show geometrical isomerism. This point is also very important. Now, if I'm talking about octahedral cases, right? So octahedral complexes of the type Ma3B3, octahedral means coordination number having 6. So Ma3B3, MAA2A2, MAB3, these all show geometrical isomerism. And the similar way, if I'm talking about the MAA3 And cis MAA2, A2 and AB3, they show optical isomerism as well. So these all points are related to their stereoisomerism, right? Whether it will show geometrical isomerism or optical isomerism. So here one important note here now, tetrahedral complexes do not show geometrical isomerism. This point must be remembered, right? Okay. Now, let's move to the next point, and this is very easy. Okay, try to understand and try to learn this as well. Coordination compound containing ambident ligands show linkage isomerism. Sometimes question were asked if complexes are given, and they ask identify the type of isomerism in this complex. So just observe if the ligand are ambident ligand, okay, if the ligand are present as in form of ambident like CN or NC, NO2 or SCN, these type of ligand present now, then definitely it will show linkage isomerism. Just remember this, ambident ligand means linkage isomerism, right? Okay, now similar, if I'm talking about CONS3 5NO2 CONS3 ONO, these are the example of which type of isomerism beta? Yes, these are the example of ambident ligand. Okay, why they are called ambident ligand present here, and they will show linkage isomerism. Why beta? Because just observe carefully now, NO2 and ONO are obtained, and these are obtained in the form of yellow and red color compound. On the similar way, coordination compound containing two coordination entity show coordination isomerism. For example, in this question, just observe that that is CONS3, one coordination quantity, and this is CrCN6, another. And this one, this in this two example, what is the difference, beta? Just observe carefully. Here NH3 with the cobalt, and this will replace with the CN in the next structure. So these type of isomerism are known as coordination isomerism. Just remember this, right? Shall we move to the next? Yeah. Okay. Now, coordination compound produce different ions in solution state and show ionization isomerism. If I'm talking about these type of isomerism like CONS3SO4Br and CONS3 5BrSO4, we know that in its solution, so the first one will give SO4 ion, right? In this, they sorry, first one will give Br ion, okay, and the second will give SO4 ion. So they will give two different ions, right? So the coordination compound produce different ions in solution state, show which type of isomerism, that is ionization isomerism, right? Is it clear to everyone? Okay. On the similar basis, the coordination compound containing ligand H2O show hydrate isomerism. For example, these example there containing H2O, they having 6 H2O, they having 5 H2O, 1 H2O is outside the square bracket. So they are called solvate isomerism, or we say hydrate isomerism. So total 4 isomerism. If I'm talking about the structural isomerism, so there are total 4. The first one is yes. Which one is the first? I'm talking about structural isomerism only. The first one is, yes, the first one is our linkage isomerism, okay, in which the ambident ligand we use. The second one is, that is coordination isomerism, in which two different coordination entity are used. And the third one is ionization isomerism, which produce different ions, right? Which produce different ions. And the last one is a hydrate isomerism, or we say this is solvate isomerism, right? So these are the examples of structural isomerism. I hope it is clear to everyone. If you have any doubt better related to this isomerism now, please ask me. Okay, please ask me any doubt related to this. Any doubt? No? Okay. So this is all about the isomerism part, right? So I'm going to reply as well. Okay, if you have any doubt related to this, you can watch. You can just give me a message or in chat box. I'll definitely reply to you all. Okay. Now, next, move to this, and this one is going to be very important. That is coordination number to in this we are going to understand totally about the VVT theory, CFT theory and all, right? So let's start with this. If the coordination number is 2, they can show sp hybridization and the geometry is also linear. For example, if I'm talking about like this, this having a metal and this having a ligand like this, okay? So these type of complexes show sp hybridization and having linear geometry. Similar way, if I'm talking about the coordination number is equal to 4, then it have a two criteria, right? Whenever the coordination number is 4, it will be two shape. Either it will be sp3 or dsp2. If the hybridization is sp3, then their shape is tetrahedral. And if the hybridization is dsp2, then its shape is square planar geometry. Okay? Is it clear to all? Right. Now, coordination number 5 indicate it can show DSP2 or SP3 hybridization and the shape is trigonal bipyramidal geometry, that is TBP. In our syllabus, we are mainly going to focus only on two type of high structure hybridization, that is the coordination number 4 having either a tetrahedral or a square planar or octahedral complexes. So we are going to discuss only two complexes, either tetrahedral or square planar, or we say octahedral complexes, right? Now, the coordination number of octahedral complexes is 6 and it also having two different hybridization, either it will be D2sp3 or we say sp3d2, right? Now the magnetic moment of coordination compound can be measured by the magnetic susceptibility experiment. So by this we can calculate the magnetic moment of the coordination compound. Now, if I'm talking about these three particular complexes now, they are fall in the category of D2sp3 haptide and they are also known as the inner orbital complex. So how can you identify which one is the inner orbital complex, which one is a low spin, high spin, whether it is a D2sp3 or sp3d2? Just remember one simple trick here, beta. What? If coordination number is 6, right? So it having two type of shape. Either it will be D2sp3 or it will be sp3d2, right? So either it will be D2sp3 or sp3d2. Now, if I am talking about D2sp3, so when the shape become D2S, when the hybridization or shape become D2sp3 beta, when the ligand is strong, whenever in the presence of a strong ligand, always hybridization is D2sp3. Where in case of weak ligand, the hybridization is sp3d2. Now, if the strong ligand are present, and hybridization is D2sp3, then it is known as inner orbital complex. Then it is known as inner orbital complex. Why beta it is known as inner orbital complex? Tell me. Because in this only inner 3D orbital are takes place in hybridization. Where in case of sp3d2, the 4D, that is the outer d orbital, comes into the picture and they participate in the hybridization formation. So that's why they are called inner orbital complex. One more important thing, if the complex are inner orbital now, then it must be low spin. It having low spin. And what does mean by this term low spin beta? Low spin means they having minimum unpaired of electron, or we say less magnetic moment. Less magnetic moment, because magnetic moment depends upon number of unpaired electrons. Number of unpaired electron. So unpaired electrons, if the number of unpaired electron is less, then magnetic moment is also less. So these all points are interrelated to each other. Please try to learn this point and try to understand the concept behind this, right? Okay. Similar. Now it's your turn. Now tell me what happened in case of sp3d2. Yes, beta. Now tell me what happened in case of sp3d2. Yeah. If the ligand is weak, then definitely hybridization is going to be sp3d2. In this, they are inner orbital, they are outer orbital, right? They form outer orbital. And low spin, they form high spin. High spin means what, beta? Yeah, high spin means what? They having more number of unpaired electrons. If the number of unpaired electron more, then having more magnetic moment. If magnetic moment is more, then having more number of unpaired electron, or we can say their magnetic susceptibility or magnetic moment is very, very high. So this is the important tricks and a basic concept behind this. How will you understand the type of complexes, whether it will form D2sp3 or sp32. Later I am going to explain how to learn the spectrochemical series as well. Okay, because many of the students are facing problem to remember, sir, how we'll know which one is a strong ligand and which one is a weak ligand, because the spectrochemical series is very large. How will I remember? So don't worry, no worries. I am going to explain the trick as well, so that you can learn the a spectrochemical series in a very good way and very decent way, and just in a few seconds you are able to identify which ligand is weak and which ligand is strong, right? Now, so shall I move to the next? Okay, so these are the D2sp3, and D2sp3, it must be inner orbital. Now, if this is a weak ligand. These all are the weak ligand. Cl, F, F. So they all form sp3 D2 hybridization and outer orbital complex. Similar, if I'm talking about the coordination number 4, that is in case of tetrahedral. So that is NiCO4, NiCl4, NiCN4. So out of these, NiCO4, this is basically the exception here, because cobalt is a strong ligand. Even they're supposed to be D2 DsP2 hybridization, but instead of this, they form sp3 hybridization. And this, there is some logic behind this. We are going to see that, okay, while doing the question. Now, Cl is a weak ligand, so the geometry is similar, that is sp3. Now, Cn is a strong ligand, then the geometry is obvious, it will be dsp2, right? Now, the magnetic, if you want to calculate the magnetic moment of NiCO, NiCl, NiCl4, now they all are diamagnetic in nature, right? So these, because they do not have unpaired number of electron. If they do not have unpaired electron, it must be diamagnetic. For paramagnetic, it must contain number of unpaired electron. I hope is it clear to everyone. If you have any doubt, beta, no? Yeah, clear? Okay. Now, this is very important, and try to understand this in a very good way, right? So, according to CFT, the bond between metal and ligand is purely electrostatic in nature. Okay, if I'm talking about VVT theory, in VVT, they are saying metal ligand bond are formed by the overlapping of the orbitals. But what the CFT indicates that the metal ligand bond is purely electrostatic in nature. It means, according to CFT, the anionic ligand are act as a point charges. Okay, and according to CFT, natural ligand are a point dipole. Obvious. If some students are asked, sir, if you are saying that ligand act as a point charges, and if they having any kind of negative anionic ligand, we understand they act as a point charge. But what about the neutral ones? For example, if I'm talking H2O also act as a ligand, then how can you say that H2O do not have any kind of charge? So how can you say that H2O act as a ligand? So beta, H2O having polar in nature, so they develop polarity, that is minus and positive charge. And through this, they act as a charge, point charge, right? So according to the CFT, neutral ligands are act as a point dipole, right? Now, the most important thing is the energy of d orbital in the octahedral complexes, that is dx square y square is equal to dz square and greater than dxxy, dyx, dxz. That is called T2G. Similar, the energy of d orbital in the tetrahedral complexes is like that. Okay, so how will you draw the complexes now? Let me draw, and you can understand in a better way. If I'm talking about CFT, right, and I'm talking about the octahedral splitting, then this is known as EG. Okay, this is known as EG. and this is known as T2G, right? This is known as T2G. Now, two cases arise here. Case number one, if the ligand is strong, if the ligand is strong, it means if a strong ligand are present, then this is splitting energy, that is delta O, then this delta O is more, right? If the strong ligand is present, then this delta O is more. Now, if this delta O is more, then how will you fill this 4 electrons, beta? Like that, okay? That is 1 electron, 2 electron, 3 electron. This 4 electron, whether it will go to Eg or remain in T2G, it totally depends upon the delta O, that is splitting energy. If the splitting energy is more, then this 4 electron will never go to the Eg orbital. It will be remain in T2G orbital itself, right? So this is totally depend upon the energy gap, that is octahedral splitting energy, and octahedral splitting energy in turns depend upon the type of ligand. So if the ligand is strong, then what is the configuration? Then the configuration is like कितना हो जाएगा configuration? Then the configuration is like this will become T2G4, right? And EZ0. T2G4 and EZ0. There is no electron in Eg orbital, right? Similar, if I'm talking about when the ligand is weak, in case of weak ligand, okay? So this is case number 2. I'm talking about the weak ligand. If the ligand is weak, okay, so if the ligand is weak now, then what happen if you want to write the electronic configuration of D4, then it will be like 1 electron, 2 electron, 3 electron, 4 electrons will go to the upper level, because here the splitting is not much more. Okay, so if the splitting is not so high, and this splitting depends upon the weak ligand. So if the ligand is weak, then the splitting is much more, and the fourth electron will go to the upper level, that is Eg level. So what is the electronic configuration here, beta? That is T2G3 and Eg1. So this point must be remembered, right? So I guess इसको reverse करो बेटा. This is not the correct one. This is the correct one. That is the energy of dx square y square is equal to dz square Eg, and it will be greater than dxy, dyz, and dz. That is in case of octahedral complexes. And in tetrahedral complexes now, in case of tetrahedral complexes, this will follow this order, right? That is the energy of dxy, dyz, and dxz is much more. And there is a reason behind this. So we're not going to explain this reason in this class itself, because this is a crash course and we want to summarize it as quickly as we do, right? So that we can solve some questions also. Now, the next one is the strength of the ligand according to the spectrochemical series. So many of you facing such many problems related to this sequence. Okay, how will I remember the sequence? So I'm here to explain you or give you some trick. By using this trick, you can easily remember this. For example, what is the trick here? This trick is basically for remembering the spectrochemical series. That is I. Okay, this is I Barbadi. Okay, I Barbadi Sunny class से फरार. Okay, so this is I बर्बादी सनी class से फरार. Oh, ऑक्सेलेटो, ओ ऑक्सेलेटो पानी सुनो, ओ ऑक्सेलेटो पानी सुनो, EDTA and ammonia, EDTA and ammonia in Canada and Colombo, Canada and Colombo, right? So this is the trick how you can remember this spectrochemical series, that is I Barbadi Sunny class se Farar. O-oxalato, pani suno, ADT and ammonia in Canada and Colombo. So just remembering this last two words now, that is ammonia, ADTA and ammonia in Canada and Colombo. So through this Canada and Colombo, you can learn like cyanide and cobalt in and ammonia. These are the strongest ligand, right? And similar, I barbadi like iodine, bromine, sunny, class se farar, like these are the weak ligand. So by using this trick, you can learn this, right? Okay. Now let's move to the next question. I already explained this, so there is no need to read this point. That is the ligand of delta is greater than P is known as a weak field ligand, and so on. This one is very important, and in last year itself, this year itself, that is in 2023 Jan session, questions coming from this topic. Questions were coming from this topic, like the relation between tetrahedral complexes and octahedral complexes. So what is the relationship between this? In your yesterday exam also, one questions are coming from this topic, that is the relationship between delta T and delta O. So this is a very simple relation, beta, that is delta T is equal to 4 by 9 times of delta O, right? So delta T is equal to 4 by 9 times of delta O. And the crystal field theory attributes the color of the coordination compound to DD transition of the electron. For example, this complex is having a pale blue color, this is blue or a purple color, this is a violet color. So it will explain the color of this compound, right? Now, the next is that is they are basically from metal carbonyl compounds. So ruby is a L2O3 containing 0.5 to 1% of chromium 3 ions. In emerald, Cr3 ions are in octahedral sites of the mineral barrel. The metal carbon bond in a metal carbonyl possess sigma and pi character. These point must be remembered. This is one is the important point. Okay. The metal carbon bond in the metal carbonyl possess sigma and pi character. The metal carbon pi bond is found by the donation of pair of electron from metal to the vacant anti-bonding orbital of the CO, and the metal to ligand bond creates a synergic effect. Yani if the reverse is takes place now, if the electron is transferred not from ligand to metal, but from metal to ligand, then it creates a synergic effect. So these are all the important point, and in this I explain all the important point related to this chapter. Now next see some more points, like FeCO5 and CrCO6 are a TVP and octahedral structure. MnTCO10 is made up of the two square pyramidal units and joined by MN-MN bond. As on the same way, CO2CO8 has a CO-CO bond. Hardness of water is estimated by the simple titration with the Na2-EDTA. This point is also important. EDTA play an important role in softening of hard water. In the solution of AuCN2, gold can be separated by addition of zinc. So these are the application of coordination complexes. The Wilson catalyst is used for the hydrogenation of alkene is this, RHPPS3Cl, right? Now, in a photography hyposolution, we dissolve AgBr to form a complex called AgS2O3 twice 3 negative. And EDTA is also used in treatment of lead poisoning. If the someone suffers from lead poisoning, then in this EDTA used as a treatment. Now, the growth of tumors are effectively inhibited by cisplatin complexes. So the growth of tumors are effectively inhibited by the cisplatin complex. So this is very important, right? So cisplatin complexes, they act as a growth of tumor. Yani they are the anti-cancer drugs. Now the central atom in the chlorophyll is what? That is magnesium. And the central atom in the hemoglobin is iron, as we all know. The central atom in vitamin is cobalt. So these all are related to this coordination chapter itself. Excess of copper and iron are removed by the chelating ligand D-penicillinamine and dextroferoxime B. Coordination compounds are used in a medical chemistry, electroplating, and textile dyeing. So these all are the application of this. Okay, so I hope, is it clear to you? I'll try my best to explain this chapter in a such a way that you are able to solve a many question and remember the important point as well. I was also share with you some tips and tricks. By using this also now you can remember the concept and it will really help in your examination for the solving question point of view, right? So now let's discuss some question. Okay, so now let's discuss some question that were coming in the previous examination. Here I'm including the last 2 3 years questions, generally from the coordination compound, right? So let's start with this. And what type of question? So the what the first question asked, beta? Yeah. What the first question? Yeah. This one asks the primary and the secondary valency of cobalt respectively in this complexes. You have to identify the primary and the secondary complexes. So which will give, which will tell about the primary and secondary valency, beta? That is Warner theory. So what is the concept behind here now? This is the Warner theory. So Warner was the first who tell about the coordination complexes. Like, so they're saying the coordination complexes possess two type of valency. One is called primary valency and the second one is called secondary valency. Primary valency are satisfied by which oxidation number, and the secondary valency that is equivalent to coordination number. So out of these, just try to identify what is the coordination number of these complexes. Coordination number means number of ligand which is directly attached to the central atom. So here 5 amine, that is NH3 atom and 1 chlorine. So the coordination number here is 6. So coordination number is 6 and this is called secondary valency. Remember this. Secondary valency is always equivalent to coordination number. Similar way, what is the oxidation number of cobalt here, beta? That is cobalt X. We know that NH3 having a 0 charge, Cl having -1 charge, and again Cl having -1 into 2 -2 is equal to 0. So X comes out to be what, beta? That is +3. So this is the oxidation state, and oxidation state represent the primary valency. So oxidation state means primary valency, and the coordination number means secondary valency. So the overall answer is, which option is correct, beta? Which option is correct out of these three? Two? Yes, that is the primary valency is 3 and secondary valency is 6. That is option number 4. That is option number D is absolutely correct. I hope is it clear to everyone, right? Okay. Shall we proceed to next question? Yeah. Now, in this question, they are asking the d electron configuration of COCl4 twice in tetrahedral crystal field splitting is EmT2n. What is the sum of Mn? Number of electron. So we already discussed now in case of tetrahedral. In case of tetrahedral, how will you write, beta, electronic configuration? So I already explained you in case of tetrahedral is just opposite to that of octahedral. Like Eg come downward and Eg having energy lesser than T2G. Right. So T2G having more energy in case of tetrahedral, whereas case in octahedral, Eg having more energy than T2G. So this is the complex, right? So what is the complex here? That is a COCl4 twice negative. So what is the oxidation number here, beta? That is X. Okay, this is X. And this is what? This is -4 is equal to -2. So what is the oxidation state? That is +2. So cobalt is in +2 form. Always remember for doing coordination chemistry questions or a D block, always remember 3D series, right? So please remember this series because this series really help you in solving the question. What is the 3D series, beta? That is, I'm also going to share one trick with you guys so that you can remember 3D series as well, right? First, let me write and then I'm going to explain the how will you remember this series. Okay. Just like this, you can also write. So what is the trick behind this, beta? I'm using one simple trick, that is science teacher very cruel. Science teacher very cruel. Mange fair copy nickel copper j. Right? So science teacher very cruel. Mange fair copy nickel copper j. Okay. So by this way, you can remember this. Science teacher. Science teacher, very cruel. Mange fair copy. Mange fair copy. So science teacher, very cruel. Mange fair copy. Nickel copper zinc. Nickel copper zinc. So this is how you can remember this series, right? So remember everyone in +2 oxidation state itself, right? Everyone in +2. So +2 for scandium, it will be 3D1. In +2 titanium, it will be 3D2 and so on up to 3D10. So here the oxidation state of cobalt comes out to be what? +2. Cobalt line, science teacher, very cruel, mange fair copy. Science teacher, very cruel, mange fair copy. That is 3D7. Clear? So how to remember this 3D7? Just write this: 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, and 6 electron and 7 electrons, right? So how many of they having T2G and EG electronic configuration beta? In EG, they having 4 electron, and in T2G they having 3 electron, right? So in EG they having 4 electron, in T2G they having 3 electron. So what is the value here? That is 3 plus 4, that is 7. So this is the final answer. It is clear to all? That is 3 plus 4, that is 7. So 7 is the correct answer. So for this, the correct answer is 7, right? Okay. So I hope, is it clear to everyone? There is no problem related to this? Yeah. Okay. Now, next move to the next question. That is, which of the following cannot be explained by the crystal field theory? Okay. So which of the following cannot be explained by the crystal field theory? That is the order of a spectrochemical series. Yes. It can be explained by this. Magnetic properties of the transition metal, it also explained by this. The next one is color of the metal complexes, it also explained by this series. So the remaining option is option number 4. This, that is stability of the metal complexes, cannot be explained by the crystal field theory, right? So out of this 4 option, which of the following cannot be explained by the crystal field theory? That is a stability of the metal complexes, right? So this is the correct answer for this question. I hope it is clear to everyone. Yeah. Now, next move to the next question. That is, all the alkyl metal hydrides are ionic solid. Okay. Now, the hybridization and the magnetic behavior of the cobalt ion in CuNH3 complexes respectively are. You have to identify the hybridization and magnetic behavior. So this is the case of what? Octahedral. So in our case of octahedral, we have a splitting like T2G and EG. T2G and EG. Now cobalt and NH3. So cobalt, NH3. So we know that NH3, 6 number of ligands, and this is a +3. So what is the oxidation state of cobalt here, beta? Cobalt having, cobalt having +3 oxidation state. Okay, how? Because NH3 having 0 charge, so total charge in the complex is +3. So in +3, we already stated na, science teacher, very cruel, mange fair copy. In +2, they having 3D7. Then +3, they having 3D6. And what about ammonia? So we know that ammonia is what? That is, ammonia is a weak ligand. So for weak ligand, na, how will you write this? Just tell me. Beta, if I'm talking about ammonia, whether it is a weak ligand or a strong ligand, tell me first. Okay. So according to the spectrochemical series now, that is science, that is Hyperbati, Sunny, classifier, O oxalate to Pani Suno, EDTA, ammonia in Canada, Colombo. So ammonia is a strong ligand, okay? Because ammonia lie in the right hand side. So ammonia is a strong ligand, not weak. So in case of a strong ligand, this splitting is much more. This is splitting is much more. So how will you write the 3D6? That is 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, 6 electron. So the shape become this d orbital is remaining vacant. So the shape become D2sp3. Okay, we already discussed in terms of a strong ligand, the hybridization is always D2sp3. And is there any unpaired of electron? Is there any unpaired electron? No. So if there is no unpaired electron, now it means what? It means they are diamagnetic in nature. It means they are diamagnetic. So which option is correct, beta? Out of these 3, 4 options, which one is correct? That is option number 3, right? That is it having D2sp3 hybridization as well as they are diamagnetic in nature. Okay, so this one is the absolutely correct. Now, next move to the next question. That is in this question, what they ask now, the number of paramagnetic species from the following complexes. Okay, so you have to identify the number of paramagnetic complexes. Okay, now if I'm talking about NiCN4, so we know that NiCN4 having CN having a strong ligand, so having shape D2sp. So it do not have any unpaired number of electron, right? NiCl4 is also not having unpaired electron. NiCl4, yes, they having unpaired electron. Copper H3 4, and this one is FeCN6 and FeS2O6. So you have to calculate for each one. Okay, if I'm talking about NiCN4, this will be diamagnetic. Okay, because they are the strong ligand. NiCO4, this is also diamagnetic due to presence of strong ligand. This will having unpaired electron because weak ligand are present. So this is paramagnetic in nature. FeCN6, again they are a strong ligand, so they are also diamagnetic in nature, right? If I'm talking about the copper Ns34, so yeah, they having one unpaired electron, so this will show paramagnetic. Now, FeCl6 also having one unpaired electron because they are the oxidation state, the whole charge is -3 given, na? So it having one unpaired electron, and FeH2O also having one unpaired electron. So out of this 1, 2, 3, 4, 5, 6, 7, only 4 having unpaired electron, and these 4 act as the paramagnetic species. So the correct answer for this question is 4. Okay, just try to solve this as I earlier solved the question related to CFT and VVT, right? So we can easily understand how will you got to know whether NiCl4 having unpaired electron or not. Okay, so it's not big deal. Now, the notion next question is you have to identify, beta, what you have to identify, that is match the list 1 with list 2. This type of questions really coming in your examination nowadays. So how to solve this question, right? So you have in list 1 coordination entity and list 2 wavelength of the light absorbed, and you just have to match them. Okay. So just do one thing. Na? We know that delta O is equal to HC upon lambda. That is HC upon lambda. Just remember this formula. It means delta O is inversely proportional to lambda, right? Inversely proportional to lambda. It means if complex is having more delta O, that is more what do you mean by this on delta O? That is more energy gap, right? If the more octahedral splitting is there, then wavelength is minimum, right? And this itself depend upon the type of ligand. If the ligand is strong, if the ligand is a strong ligand, then splitting is more. If the splitting is more, then the wavelength is minimum. So just use this concept here, right? So if I'm talking about in the first case, that is the Cl and NS3. So NS3 having a weak or a strong ligand. So it weak, a strong ligand. So if the two ligands are present, one is a strong and one is a weak, then consider the effect of a strong one. That is NS3. So it means it is totally strong ligand. If this is a strong ligand, it means their splitting is more and wavelength is minimum. So out of these 5, which one is the strongest ligand? So here the Cn is the strongest ligand, right? Cn is the strongest ligand. It means Cn having less wavelengths. Minimum wavelength is what? 310. It means Cn, that is this one, belong to this. Okay, that is C belong to first. So in which case C belong to first, beta? Yeah, in option number 2 and option number 4. Now the next strong ligand is ammonia, that is NH3. Okay, so NH3 belong to next nearest is 475. So this one. Okay, and this is NH3. Next is this one, and this is weak ligand. So this is the correct. So which is the correct option, beta? That is option number 2. So just by using this formula, na only H naught is equal to SC, lambda naught is equal to SC upon lambda, we find how we can calculate what is the relationship between this. Okay, so this is how we can actually calculate the relationship between this wavelength and the splitting energy. So I hope you find no difficulty in solving this question also. Is it very simple? Yeah. Is it simple, beta? Right. Okay. Now one more question, that is you have to this will be, I guess, last question, right? So total number of moles of AgCl precipitated on the addition of excess of AgNO3 to the 1 mole of each of the following. So in such type of question, this question also belong to the Warner's theory itself. So just calculate the number of atom which is present outside the coordination sphere. For this, for example, in this case, one chlorine atom is present, right? In this case, two chlorine atom is present outside the coordination sphere. In this, zero, and in this also two is present. So you have to calculate now. So if you treat this with AgNO3, then here 1 mole of AgCl is precipitated. So 1 mole of AgCl. Here also 2 mole of AgCl is precipitated. Here also 0 mole. Here also 2 mole. So how many moles of AgCl are precipitated, beta? Total. So 2 mole to 4 plus 1, that is total 5 mole. So total 5 mole of AgCl are precipitated. So the correct answer is 5 only. Because we know now only these atom, that is the atom which is present outside the coordination sphere, are ionizable in nature. Because coordination complexes are not ionizable in nature. They cannot be broken into a further part upon hydration, or we say in their aqueous solution. So only the atom which is found outside the coordination sphere are take part in the reaction with the AgNO3, right? So this is the correct. So today we discuss entire chapter of coordination chemistry in a very summarized way, or in a very short or important way. I'm cover every topic. I'm not I'm not miss any topic related to this chapter, but try to cover all the topic in a very short and very decent way, so that you can able to solve the questions that were coming in the your previous examination, and it will really help in your examination. And I'll explain 4-5 PYQ as well. So try to do as much as you can by just using the concept which I teach you in the class. Okay. Once you started practicing now, then you can easily solve many questions related to this chapter, right? So let's end the today class with this question, and we are going to meet you again in the next class where we'll discuss some another chapter, right? So just take care and try to solve the questions and just enjoy your study, nothing else, right? Okay, so we'll meet you in the next class. Till, take care. Bye.